Okay, so if we want to make a second stage that creates a perfectly circular orbit in one burn, then we need to do a bit of maths. First, we need to recognize that a circular orbit is not any different to just a circular path on Earth. And for that, you'll need a centripetal acceleration that constantly keeps it in a circle. And for this example, we've got a tennis ball on a totem tennis post that goes around in a circle, and as the velocity goes in one direction, the centripetal acceleration is perpendicular and towards the center, towards the center of the circle. And we can see that's not much different to an orbit around a planet. We've got sideways velocity and some sort of inwards acceleration, which in this case is gravity. And there's a simple sort of formula to find out the magnitude of that acceleration, and it's a equals v squared on r. And if we solve for v, then we get v equals the square root of acceleration times the radius. And that is the velocity we need to travel at to get a perfectly circular orbit. The thing is, once we ditch the first stage, we haven't got a perfectly circular orbit. We've got a parabola like this, which hopefully the apoapsis should be outside the atmosphere, which means that we're basically touching the edge of this circle at this point here. So we know our radius is the apoapsis. So what we can do is we can figure out how fast we need to go from this point, how much faster we need to be going at this point to get a perfectly circular orbit, because at this point we're going too slow to have an orbit. So we need to add some velocity at this point. What we can do is the velocity we add, or delta v, equals this orbital velocity minus this velocity we're already going. And we can find that using the conservation of energy, and it's mgh at this point here, at point 1. Point 1 is just as we leave the atmosphere, and there's no atmosphere pressure at all, atmospheric pressure. So that would be point 1, and we can automatically trigger when that happens. So this is point 1, just outside the atmosphere, and this is point 2 at our apoapsis. And this point here, this thing here, velocity 1, is the combination of velocities, vertical and lateral. That's just sum of energy we have, sum of kinetic energy we have at this point. But at the apoapsis, we can just use the lateral velocity, because at the peak of a parabola, peak of a trajectory, there is no vertical velocity. So we know that Vy equals 0. And at this point we can find Vx. We need to know the relation. There we are. V2 equals Vx. However, the problem is that g isn't constant. It's a function of big G, it's a constant, divided by the distance you are from the center of the planet. And in this case we can call that Fr, because it's a function of r. And to find the average G, we need to use this formula here. And we know these two variables, these three variables, R1, R0, and R2. R1 being this point above the atmosphere, which is the radius of the planet plus the height above sea level. And we know the radius of the planet, 124,000 kilometers. And we know the apoapsis, which is R0 plus apoapsis is R2. That's the R at point 2. So we can find that this function here will solve for G1, G bar 1, and this function here will solve for G bar 2. And now that we know those, we can make them a variable and just put them back into our equation. There we are. And we know H2 is our apoapsis. And therefore, the velocity that we will be traveling at the peak of our parabola will be the square root of 2 times G bar 1 times H1 plus V1 squared minus 2 G bar 2 times H2. And V2 here is also our Vx, which is up here, our Vx. However, we now know our delta V. The problem is we can't immediately gain that velocity. It takes a bit of time to implement it, to thrust to that speed. So we need to know how long it takes, and that's where we need to find burn time. We know delta V, and we can use momentum. We can use force times time equals mass times velocity. And in this case, we know our delta V, we know our mass. However, mass isn't constant because as we're accelerating, we're using up fuel, which means the rocket's getting lighter. We have less mass, so m isn't constant. And because it's not a curve or anything, we can use just a nice linear, this formula to find the average. So m0 here, or m dot, whatever, is the fuel rate consumption in kilograms per second. So that once we can find that out, we know the burn time of the stage, and we have the mass of the fuel divided by the burn time of the stage equals our fuel rate consumption. So then once we know this formula, then we can solve for t, and t equals 2m delta V divided by 2f plus delta V mo. However, that's not everything. We still need to know when to start the burn. We can't start the burn immediately once we're in the atmosphere, once we're out of the atmosphere, because that would have a very weird parabola, very weird orbit. We need to have it so we have that horizontal velocity at the peak of our parabola. So what we can do is we know our burn time, how long it's going to take to burn, so we can have it so the middle of the burn is at the apoapsis. So you have just a little bit before and just a little bit after, and it averages out just to sort of in the middle there. So t on 2. There we go. When we start the burn, when we are t on 2 seconds from apoapsis. And we can kind of cheat for when to turn off the engine is when the velocity, our sideways velocity, equals the orbital velocity. But there is a little bit of an annoying thing with these engines, is that they don't turn off immediately. They sort of spool down. So you have to have a little bit of cool down, and it changes for different rockets, different engines. But for this one that I've tested, it's about 250 meters per second. You get a little bit, in vacuum, you have 250 meters per second added to your velocity after you've shut down the engine. So the last thing we need to know is where to burn. Where should we point the rocket when we start our burn? And when we have our parabola, we can't say prograde, we can't say just face forwards, because we'll end up shooting off into the sky. That won't work. We have to have it sort of pointing parallel to the surface of the planet, like this, parallel to the surface of the planet. And that is just pitch 0. We're not pointing up or pointing down, we're pointing exactly sideways. So that's where we need to go, pitch 0. And if that all works, then we should have a roundabout circular orbit.